Hi, my name is Łukasz Langa.
And my name is Pablo Galindo.
And this is the core.py podcast, a new podcast where we discuss internals of CPYTHON and our adventures in making a new version of your favorite programming language. Today, we'll be talking about imports and recent changes to Python.
The real question is when it will be time to stop saying a new podcast.
Well, maybe it's not time yet. Like, we are already 2 episodes in, but now this is the 3rd, so this is still a little soon, I guess.
We don't know how to count to 4, so it's fine.
Now you cursed us. Okay, we need to get to the 4th episode. Oh no, Now I'm scared. Or we can start naming the episodes 3.1, 3.2, 3.3, and so on.
And as a release manager, I missed the opportunity to start naming the releases, like, Slow Turtle or like Fast Wolf or like, all these funny
Bionic
names.
Beetle, yeah, and so on and so on.
Yeah.
Right. I'm terrible at naming things, so I was happy not to have to do that. So, kind of to each his own.
The real question is, are you good at importing things, Łukasz?
Right. I am efficient at importing things that I need to import. Sometimes the import system will be a little stubborn, but usually I can convince it to do what I need. But I recently actually had to help somebody with an issue that, looked like an import system issue, and it turned out to be just a miscompiled SO and a bunch of files that were just lying around inside packages. So what was happening was weirder than the person thought, because some of the not actually installed modules left directories behind. And because of this, the import system now tried to import this, and weird things were happening.
Right.
So I thought, how about we actually talk about the import system in Python and how it does things just for a while? Like, we don't need to go into too much detail there, but just a bit about like how this thing is constructed, because it is surprisingly complex. You just write import OS, you don't really think about what is happening, or import NumPy. But there is quite a lot of depth beneath.
Right, and I think it's one of these parts of CPython or Python in general, when if you joke and say, don't worry, nobody really understands what's going on when you import something, they might be true, like they might be right? Like maybe there is, a lot of people that understand 80% of it, but I'm sure there is some dark corner of what is executed when you import something that many people don't know.
So how about we actually talk about the high level?
Right. The summary is actually quite easy, at least because we have worked quite hard to hide all the dirt under the covers and all the names.
Yeah.
But the summary is very easy. When you say, I want to import something, the first thing the Python does is check if it's already imported, right? And this is, we store the modules in sys.modules. And if it's there, you just return it. You can actually use this hack to just put something there and it will be returned. Like if you put a list and then you import something, it will be returned from sys.modules because we just checked there. Obviously, most of the modules will not be imported when you start Python. So the next thing Python does is so we need to find it. So it sets the import path, I think, to none, which is quite surprising because sometimes when something goes wrong, that none appears somewhere. So it's good to know that the first thing we do is setting the module search path to none. And then what we do is that we need to figure out all the, if you're importing from somewhere. So you say, from numpy.arrays import something. Obviously, if you have not imported numpy before, you need to import it now because, there is some dependencies there. So if the module has a parent module, you need to import first the parent module. So this process is obviously recursive. And then you need to set a bunch of specific attributes like underscore path and all these things depending on the different dots. Then once you have taken care of all of that, then the funny words start. So the thing that you need to do right now is that find the module spec, which Łukasz, I'm sure you're going to describe it in a second.
Sure.
But once you find the module spec, which basically is like half of where the module is and like how to load it.
Yeah.
But when you find it, there is like an algorithm that works there just to know how to find the module and how to load it. But once you have it, then you start calling it. Like, so this is an object that tells you like how to, open these modules, find them and execute them. But when and everyone will have a different one, right? So it's not the same to import a .py object that to import a set object. So, there is different specs here.
Yep.
And when you have the module, you call the spec to load it and you add it to the dictionary of the parent module because obviously, if you have numpy.array, then it has to be an array attribute on the module numpy. And after that, you put it in sys.modules and you just return it. So when you say import something, then there you go.
Cool. So let's go into a little bit more detail. Importers in Python are actually split into two things. Like first, before you import the module, you need to find it. So we actually have those objects called finders, and you can implement your own and put it in sys.metapath that will allow you to find where a module lives. Usually it either is built in or it's available in some frozen state that we're going to talk about later, or it's just on the file system. But it can also be in a zip file. It can also be in a database if you implement that. So, if you want to, you can actually plug into the import system to extend it. So the finders are only kind of interested in just localizing, like where is the actual data that I need to fetch to actually be able to, load a module, but it doesn't do the loading. That's actually something that is happening later.
Right.
So what the finder is returning is it's returning a module spec, and that is all the metadata that is needed for a loader to actually do the loading. So, now you were decoding the actual bytes or whatever and turning them into something that we can put in sys modules.
Right.
So the interesting thing about this is that beyond regular Python files storing source code or bytecode in case of PYC files, you can load Python modules from any other data structure.
Wow.
I used to work for a company that provided banking software like back in the day. That was before I was a core developer. And one requirement that we had at some point to disallow the bank itself tampering with the system was to encrypt the source code that we were providing to the customer, right? The bank was a customer.
Very responsible.
Yeah, well, yes. So, we could actually do this, and we had a PEP 302 hook that we could use for decrypting the bytes that we had with some AES key that was shipped in some SO file, so it wasn't very easily kind of findable. Obviously, if somebody wanted and they went to a debugger, they could find the actual decryption routine and they could find the key and whatnot, but it wasn't so much about making it impossible to decrypt our source code. It was about making it really inconvenient for the customer to make changes, right? Because it is extremely convenient otherwise for users of Python to just change one file and just re-execute the Python interpreter and see what's changed, right? You can put prints, but you can also just put entire new pieces of functionality or remove pieces of functionality where some feature was gated behind some, paywall or whatever else, right?
Right. Yeah, I do it all the time. I sometimes when I debugging something and the problem or is in somewhere else's package or even in the standard library, I just edit the file and I breakpoint and it breaks there. So it's very convenient to be able to edit the files.
When I'm using Visual Studio Code to actually develop CPython, every now and again it would lose, the current interpreter, which should be the one that I'm just building right now, the one that I'm working on. Like every now and again, like when you clean your state of repository, there is no python.exe on my checkout anymore. It's temporary, but it's not there. So VS Code would be like, okay, there's no interpreter, so let me find a different one. And it would find some different one. So when
I know where this is going.
Yeah, so sometimes when I'm just actually switching to some other file to just make like a short edit just to see like what I'm doing, or actually make an edit that I wanted. So to change Python, what I'm changing is I'm changing the standard library of some installed Python, like different version.
Man, I have created entire PRs in the installed version of Python, and then I do git status and there is nothing. Can you imagine the like how much time until actually like I looked at the path of VS Code? It's like, oh, you are editing
exactly
PyM, blah blah blah. Like Jesus, man, like that problem.
I am getting better at this, but still every now and again I would just look at this and it's like, this file looks a little too clean, and then I'm looking and it's 310. It's
Right.
like, oh yeah, of course it was so easy back in 310 days.
Developing is hard.
But in any case, like we were talking about imports, right? So you found a module with a finder, you loaded a module with a loader, and now you have a bunch of modules in your sys module, so you can import them, right? But that's essentially just the modules on the path that we know. And that, surprisingly, does not include any location where pip install would put new packages.
Right.
Because this is an add-on on top of built-in Python imports. In fact, that add-on is using how the import system is pluggable to add new paths and to allow for more functionality. And this is all found in site.py. Can you talk about this, Pablo?
Yeah, site.py is probably one of the dark corners when like we start dumping all the weird stuff there. Like, there is several Lovecraftian monsters lurking there. So site.py is like when all the like logic that, someone like modifying the import system says, nah, they shouldn't be here. So they put it in site.py. And right now, like site.py does a lot of things. So it basically sets up all these like, okay, like it adds side packages and certain other folders to the standard lookup path. So you install NumPy, you can actually do import NumPy, and that works. Because otherwise Python wouldn't know that, where is NumPy, right? Because this may surprise some people, pip is not actually part of CPython. That's its own thing. Like technically you could have pop and that can be as good as it, right? As long as we just say, we hardcoded here a path called side packages. You just put the stuff there, right? But like that is all that we do in CPython.
Right.
But site.py does a bunch of other weird things. For instance, do you know that when you just type Python and then you enter the Python REPL, you can do a bunch of extra things that you cannot do in normal files. For instance, you can, and this is like there is a bit of a drama regarding some of these things. So you can type exit, and then what happens when you type exit, Łukasz?
It will tell you like, if you actually want to exit, you need to call.
Exactly. Oh man, you are a core developer, right? Because you know the drill. You need to call exit because exit is not a command; it's a instant of a class called exiter. Man, software development is fantastic. So where is this exit coming from? It's certainly not a keyword. The parser doesn't understand that. So it turns out that site.py, when you start the interpreter, this file is automatically loaded. So site.py instantiates this exiter nonsense, and then it injects it into the global namespace. So when you type exit and it tells you, bad boy, you need to call exit, what you're actually seeing is the REPL of the exiter instance. How beautiful is that? And there were some people which, with a lot of, they have a real point here. That is that if you know that the user is trying to exit, well, you just don't exit, right? And, it turns out that because we implemented this with a hack and not with a proper REPL, this may be a hint of what is coming soon. Maybe we fix this. But because we implemented it with a hack, well, we cannot just exit, because if printing the exiter object just exits the interpreter, can you imagine how funny it will be that someone is printing all the objects in, the global namespace and suddenly the interpreter exits? Not a great experience.
Well, fantastic, actually. My job here is done.
You will never know what's going on. Look, I print this list and it just exits. Works as intended. But other things that it does is that it sets, like, for instance, completion in the REPL. So every time you press tab, it completes what you want. So that's the real line completion that site.py also does. It loads also site customize, which is this other file that people can put in the system, and this is more focused not to users, for people managing the Python installation. Sometimes it's you, but most of the time is the sysadmin or whatever. So to inject like custom stuff there, that is like site.py but for normal people. And yeah, it also injects helper and copyright and a bunch of things. So yes, site.py is full of marvels.
Yeah, and it already kind of imports quite a bit of things from the standard library, and it's like it's an interesting, it's an interesting piece of code in the standard library. So if you're like, okay, where does it live? Well, it is just part of the standard library, like any other module. Like you can find it in lib site.py. You can read for yourself what it is doing. So yeah, I highly recommend you do that, and to understand how is it that we actually have site packages, and why are they called site packages? Well, because of site.py.
Right. But you forgot the actual, all of these academic descriptions are cool, but the interesting thing that people probably want to know is how all the evil things that you can do with these like import system hooks and whatnot. Because if you are in control of how do I find the files and how do I execute the files, then you can do a bunch of weird stuff, right?
Yeah. So yeah, well, you said that you can import things that are not Python modules.
Right. So, for instance, the normal thing would be extension modules, but those are the boring ones. Something that you can do, you implement your own, loader in this case, probably Finder as well, because you need to change the suffix, is that you can implement a loader for, let's say, images. So you can have like, import my image.png, and it will return you a NumPy array with the image. So, you can have a super coarse Python module when you import images that way, or training data for, machine learning or whatever. That is kind of weird, and, nobody will be able to understand your code base. But actually, we do this as well in some places. For instance, CPython can actually import zip files.
Yes.
But yeah, like another example of things that you can do, which are a bit evil, that actually some people do, is to go even before all this like import system stuff and go to the codecs module. I think in the last episode we mentioned something about like this precisely. But before any of this import thing happens, you need to be able to decode the source code, right? And for that, Python has this whole codecs collection that you can also hook into it, and you can say, well, in the same way UTF-8 and other codecs, allow you to understand like what Python files are, and like to make sense of the actual characters, you can just add your own. And it cannot be a codec, actually. It can do some weird things. So some people, what they like to do is install some random codecs and literally change the source code. And that's, for instance, I think some of these hacky packages that some people like to do, like, backports or F strings or something like that. So what they do is that they install these hacky codecs, and then they change the source code. Right. So when they detect an F string, they change the source code into the actual like function call that does all the locals and all that
One
stuff.
cool thing that I saw that did use this was like at Dropbox, they had this thing called Pixel that was embedded HTML in Python. So something that, kind of React now also has in JavaScript. So like the equivalent of this in Python, where you could literally just like start opening tags and closing tags, and just directly in your source code, and it wouldn't just translate this to a string. Like those were actual Python objects and so on and so on. So this was fully traversable, and kind of could work with some other libraries that they had, but the way you expressed it was visibly HTML in your Python code, right? And the way that that worked was by hooking into codecs. So, providing a pixel codec that could actually just in time transform all this HTML into those boring, regular Python object instantiations.
I think right now there is, I mean, I don't know if soon, but I know that Guido and some other people are working on this idea of tag strings, which may be a better solution for this. So the same way now you have F strings, and then you say F, and then your string, and then your string now is magical and can, do a bunch of interpolation. So you could say HTML and then a string.
Yes.
And it will do that. It will transform the string into those HTML objects. And you can have like this will be pluggable. So you can do SQL and then a string, and it will, check that SQL is valid, or like, a linter may be able to hook into that and validate that it doesn't do weird, dependencies, injection, SQL injection, and things like that. So still, like, obviously, there is not even a PEP for this right now, but that is, I think, something that I think there is a prototype somewhere. I think tag strings is called.
Yeah. So this is interesting. And one kind of particular detail about the string prefixes is that, say, you have R strings, so like raw strings, right?
Right.
Most uses of those are in regular expressions. So in VS Code, when you're writing regular R strings, like lowercase r, it will automatically highlight the inside of that string as a regular expression. This is not something that you want every time, though, because sometimes it's really some raw string that has nothing to do with regular expressions. So if you want that and you don't want VS Code to format it that way, to highlight it like this, what you will do is you will use the uppercase R string prefix, which is the same thing for Python.
No way.
Python doesn't differentiate, but now the highlighter will understand, okay, this is actually raw, like this is uppercase raw. This is not a regular expression. So initially black, was kind of making all string prefixes kind of the same, right? It was making things consistent. And I had to like make this one special case for R uppercase because people are like, oh, this is breaking my syntax highlighting in VS
Oh
Code. And I
boy.
was like,
Oh
what?
boy.
How? But and then I learned about this kind of obscure feature, which is still there. Like to this day, you can actually see this. This is actually pretty cool. So like what I would like from the syntax highlighter personally would be for it to not even attempt, not at all, to format any braced expressions in regular strings. Just make them the same color as the entire string. Just show me that they are not evaluated, because to this day, every now and again, I would forget the F in an F string.
Right.
And VS Code is kind of lying to me. It's like, oh, look, this is nicely, formatted, because it's trying to say, okay, those are places that you can now hook into with dot format, right? Because this is what it thinks.
Right.
But like that is useless to me. Like I don't want this. What I would like is for me to understand you are not writing an F string right now. This is a regular string. Like put the F there and suddenly it highlights differently.
Right.
Because it still does, obviously, right? The actual expressions inside are more colorful, like they have different colors, but my brain doesn't register this nuance. It only registers, okay, it syntax highlights, so it's fine. It's not always fine, but yeah, well, we kind of digress. We
Well, I
kinda
think you
digress at this
mentioned
point.
you mentioned before something like too fast. You said like, oh, there is this frozen modules thing, and I don't think we explain any of this. So can you just cover like and explain a bit what are these frozen modules?
Yeah, so back in the Ice Ages,
That's how all the great stories start.
there are actually a bunch of things called freeze in Python. So just to get this out of the way, there is tools freeze, which is not what we're going to be talking about right now. Tools freeze is something like PyInstaller or, kind of PyExe or whatever, something that allows you to just bundle your code with a Python interpreter so that people who don't have Python installed on their box can run your program. This is actually pretty cool. Like you can try this out like on your own code. There are libraries built around this functionality.
Right.
We ship it as part of Python just to make sure that like we still have working functionality that allows all the hooks needed like,
Right.
for this kind of compression of your thing like to one file work. So this is not the freeze I mentioned at the start of the episode.
Right.
What we're talking about here is the ability of Python to ship with already some code objects, some module code objects preloaded into the interpreter, right? So you might think of the sys module as one that comes with Python. There is no sys.py. That one is actually even more special. It is hand-coded, but a bunch of other modules have to be part of the interpreter itself because they take part in the interpreter's initialization or for other reasons. And, this is why they are frozen. You can see this when you display the wrapper of such a module. Try ABC. ABC is a good example there. You will see that it is frozen in parentheses. You'll still find the abc.py file, but the reason why it tells you it's frozen is that if you'd made any changes to the abc.py on disk, you would notice that they are not in fact being read back. They're not being included in a restored Python process. This is because Python instead is reading from its internal frozen version of this module.
Right.
Originally, the import system in Python was written in C. And this is where all this kind of, scare of what does the import system do come from, right? Because at the time, it was very hard for us to follow the logic of the import system does this first and this next. So Brett Cannon, some 15 years back, has this idea like, how about we rewrite this in Python? And obviously, if you do this, this would be, first of all, slower. But second of all, there's some chicken and egg problem there. We are trying to make the import system that Python itself is using work. So how do we do this? So Brett devised a way where he wrote the initial crucial part of importing in Python, but that part that bootstraps the entire system needed to be included in the interpreter.
Right.
So he also added a tool that froze this part, this bootstrap part of importing, into a header file that includes essentially the same marshaled bytecode that you would get if you created a PYC file, but it is now part of the Python interpreter, making it independent of whatever is happening on the file system, and also making it much faster to actually initialize this part, because you don't have to look for it anywhere on the file system.
Right.
Now it was still kind of producing something that was equivalent with the same CAPI calls and so on in the end, but we at least could follow the logic looking at the Python file way easier. It is not regular Python in the sense that it cannot just import anything, right? Including sys, they cannot do anything. Like you inject a bunch of things to this bootstrapping importlib part. But you can still read it pretty clearly. You can still see some of those things that we were talking about in implementation, and you don't need to know C to follow it. So that was pretty cool. But that was then, right? Like that was the original story of why freezing was added to Python in the first place. But then once it was there, it was just a matter of time people would want to use it for more things, right?
Right, and actually, one of the interesting parts that happened here is one of the part of the work that the Faster Python team did in 3.11. If you type Python, just Python, or even Python -z pass, which is the smallest thing that you can do without actually doing anything. So that feels normally quite fast, right? Like we are talking about milliseconds there, but this is actually something very important for a lot of people, like how much time Python needs to just start,
right,
or even just import the bare minimum. The reason is because if you, for instance, implement a command line application, right, like just typing something like your command and then dash help just to see the help, if that feels choppy, then it's not a good experience for the user, right? Like, and I'm sure you can think about many of these command line applications that actually don't feel quite snappy because they are implemented in Python. There is different reasons, and even the ones that are more or they present more problems regarding this. They have other reasons when they are slow, but this is something that a lot of people care, like startup time, right?
Right.
And this is something that actually some people even try to fix. Even there is some discussion about who came with the first idea of the solution, but the one I remember particularly myself in the first sprint that I attended, the first CPython core developer sprint, it was the sprint that Microsoft did in Seattle. So there were some people from Facebook, in particular a gentleman called Jethu Rao. Sorry if I'm mispronouncing the name, but they basically were concerned about this, and they proposed an idea to basically make a startup faster. And the idea is that, okay, so you run your kind of profilers here, I think it was just strace or something like that, and then you just see what Python is spending the time when you start the interpreter. And it turns out that most of the time it's actually reading files. It's going to the system and then checking, is this file here? Yes, okay. Can I open the file? Yes, here, you open the file. Now can I read the file? Sure. So all these file system operations are quite slow, and are even slower in situations when the file system is slow because you are using NFS, or even like, it depends quite a lot. And even in the best case, is almost maybe not the best. So what they propose is that, okay, maybe we can identify all these files that the interpreter is opening just to start, because when the interpreter starts, it needs to open like standard library files like codex.py and like abc.py and a bunch of these. And he proposed to do the same freezing mechanism as you described, basically grabbing the Python source files, pre-compiling it to bytecode plus some data structures, and then basically transpile that information to C and then compile it inside the Python executable. So the difference is that when you start Python with this work being done, then you don't need to go to the system and then try to find the files and compile the file or the PYC files and all that stuff, because it will be already ready for you as exactly the data that you need because it was compiled when Python started. And they have like this big patch that I think Larry Hastings reviewed, or they were making it. They measured even like something like 20-30% improvement on the speed. unfortunately, that went nowhere. There was some discussion about like if this was good or bad, because like there were some concerns, as you mentioned, that you couldn't edit those Python files of the standard library, as we mentioned before, to do the hacks and the breakpoints and whatnot.
We need the hacks.
Right. Yeah. And also like, there was some things that Larry did to like search for the module in sys.path and check the dates and whatnot. But that actually ended nowhere. But then the faster CPython team, like, very recently picked the idea again. Mark Shannon apparently also did this, or a version of this, in one of the work that he did as part of his PhD thesis, or something related like that, in the HotPy project. And I think there were some other similar tools that MicroPython did. So MicroPython has also the same idea of frozen modules. That's more or less the same thing. They use MPY files or something like that. But the idea is that they identify a bunch of files that are needed at the startup, and they did this. Obviously, this becomes very complicated very soon, because if you want to freeze, let's say, abc.py, and that is importing more modules, then you need to freeze more than just abc.py, right? Yes. You need to freeze all the dependencies and dependencies of the dependencies. So that is why the file that does this process is called Deepfreeze. Maybe someone, there is some obscure reason why it's called Deepfreeze, because maybe it's frozen 2 times. I don't think so. But I think the idea is called Deepfreeze because it freezes the whole dependency chain, which is different from the other tool called freeze.
Right.
So it is the word freeze 6 million times in the build system. But this is basically what this is doing. And it creates these frozen modules inside the interpreter, and you can actually see that. Like if you do import like ABC or import collections, I don't think collections is one of them, but you get the idea. So you import one of these modules and then you just print it. So you, in the REPL, you say import ABC, and then you say ABC, enter, and it will tell you module ABC, and it will tell you it's frozen. Or frozen something, right? It's the same thing as importlib. When you import importlib, it tells you frozen importlib, and that's because it was frozen.
One of these days, I'm just gonna go and make changes to Deepfreeze so that it is using all the cores that I have. Like, it is not gonna be like an easy change. I already looked at it. Like, is there something that I can just trivially just add, process pool executor and be done with it? But no, like, it's gonna be a little more complicated. But it easily doubles my build times, like on M1 Max now. Like it's like all of this other functionality with configure that you already have, like caching for and everything, and make, that is like ridiculously fast as well now. And on top of this, we have Ccache, and on top of this, it also doesn't rebuild things that don't change. So those things like are very quick. And then you get to Deepfreeze and you wait for another 10 seconds. I know it's just 10 seconds, but kind of some people would rewrite your entire tool if you're just a few seconds too slow. So like one of these days.
Are you saying that Python is slow, Łukasz? This is what you're saying?
Maybe we should show Deepfreeze to Charlie and he's gonna rewrite it in Rust. It's gonna be rough Deepfreeze now. It's gonna be very fast. Why not, actually? All right, so that concludes the part about the import system as well as the frozen modules. Those are only tangentially related, but we decided to cover both because if you're going to be looking at the import system at any given point, you will discover the concept of frozen modules. So you're going to be interested how they came to be and how they function. So now, having this settled, let's talk about something completely different.
What's going on in CPython?
Things that happened in CPython since the last episode. And when I was gathering this, I already had an idea on like 1 or 2 changes that I was kind of involved in. So I'm like, okay, and there's going to be something to talk about. And then I looked closer and wow, like there were so many changes that we actually had to just pick some top changes. So if yours will not be mentioned, it's not that it's not important. Simply, we just had to focus on just a few.
It failed the lottery, right?
I don't know, like Pablo, let's maybe start with you. Can you talk about like some of the changes that we had? Like the biggest chunk is probably the ton of work landed like to support nogil. So let's start there.
Yeah, of course. Actually, this is quite impressive that we are this far already. I was, I think it was Victor Stinner who said that there is this. If you notice some earthquake, is because a lot of the nogil work just landed. Obviously, the things that we mentioned in the previous episode apply. This is still a build flag and whatnot. But for instance, one of the things, landed is bias reference counts. This is something that we discussed in the previous episodes. So this is already landed. The code is there, is running. We have, I think, CI also for nogil. So there is some machine somewhere. There is a bunch of buildbots, right? Like you help setting up some of the buildbots.
Yeah, like it was a little kind of complicated to set them up at first, but soon enough, like all this extra kind of setup will just not be necessary because we will be able to just call them stable. Like it is moving pretty fast, like right now, like with okay, so just to take a step back, like when we have buildbots, right, our CI servers that actually run with very many configurations and test whether Python is still in a stable state, we have a ton of different configurations that we run, and some of those we treat as like super serious parts of our infrastructure for making releases. So if any of those is read, like, that would actually stop the release. So we call those stable. There's a bunch of those. And then there's many more that, check some particular configuration or setup with some library that, for example, is competing with glibc or some other library like that. Right? And we want to run those tests as well, but if they break, it might not necessarily mean that we broke something, so we don't mark those as stable. So currently, like the free-threaded, as the Steering Council wants us to call nogil, right? The free-threaded...
There is nothing called nogil.
Yes.
It's called free-threaded, Łukasz.
Exactly.
We comply with the Steering Council.
Well, like, yeah, I should, because 50% of people on this podcast are sitting members of
watching you.
SC.
But the only purpose that I'm here is just to watch how you refer to
how many
nogil.
times did I sell nogil? But in any case, so the free-threaded build bots so far, like, they're not treated as stable. Obviously, there's a lot of change happening there, and it's under configure flag, and this is an area that is moving very quickly from unaccepted PEP, of course, but it's still not entirely stable, and we're very far from Python 3.13 for now, at least. Like, I'm pretty sure, like, famous last words, like, it's gonna be May in very quickly. But so far, like, we didn't mark them stable, but looks like we might very soon, since like biased ref counts are already in. Mimalloc was added as well, right?
Yeah, mimalloc landed as well. That's quite cool. I think we mentioned it very quickly last episode, but I don't think we went into a lot of detail.
Right.
So what is mimalloc, Łukasz?
Well, so this is the Microsoft allocator, and in fact, Christian Hymas just last year already wanted it as part of Python, not tied to free-threaded Python, but just as a way to make the allocations in Python faster. And also, thread safe, that is kind of only for threading, right? But also aware of non-uniform memory access, something that you might not really think about like when you have your phone or your laptop, but something that is actually very useful when you're running servers. So, like some of the contemporary processors like Epic from AMD and so on, and Threadrippers actually, so you can have this on the desktop, they can access their own local memory. So like a core or a processor in a multiprocessor system can access its own kind of designated memory faster than non-local memory. So there is only some pool of shared memory, but every processor also has its own. And this needs support from the operating system, but above this, the processes that are running on such an operating system need to also plug into that. So Java 7 already has a memory allocator that can work faster with those non-uniform memory accesses, so like NUMA, right?
Right.
So like a modern server, can actually use this, right? And when you have, say, containers, right? Like you can actually just make sure that they always run on the same processors, right? Or on the same cores. That's called processor affinity. That's something that we've had for quite a while.
Right.
But now you also have with NUMA memory affinity, where you can say, you just use this pool of memory. And actually combining the two allows hypervisors to actually, increase, observable performance by containers by quite a bit. There's papers by AMD about this and whatnot. But in any case, like so far, the allocator we've had, mimalloc, was entirely oblivious of all of this advancement, right? And mimalloc is something that actually allows us to tap into this. So not just for free threading, this should also be faster for server usage, which I'm pretty excited about. And we already kind of covered this when talking about PEP 703, where we have now built-in free lists with multi-sharding, there's multiple allocation heaps, and so on and so on. So it uses some atomic instructions like compare and swap. So it's not just thread safe, but it's actually efficient. And so on and so on. But, it doesn't work everywhere that CPython currently builds on, but it works on the majority of platforms. It requires...
Well, that sounds very ominous, but like it works on most modern systems. Like in the sense that you don't need like anything super, super special. Like all compilers like certainly won't work because, we require some higher C standard.
Exactly.
I think it's not as easy to say as C11 because the C standard stuff is just a mess because you can be complying with C11 but not C99 like the Microsoft compiler. I think it does, or the other way around.
The atomics that I was talking about, like, that requires a relatively recent compiler. But, kind of if you're running a relatively recent Red Hat or whatever else, like, you should be fine.
Right. I think it's AAX is one of the systems that don't support this out of the box or one of the oldest ones. But yes, like who cares about the AAX, right?
Who cares about it? Yeah.
Right, exactly. Yeah. So mimalloc is quite cool actually. I think I was working with Christian Hymes when he did the first benchmarks, and what we experienced is that the default, obviously we were not running in servers with cool NUMA, we were running off like old people laptops. Like we experienced no speed ups nor any slowdowns, which you will say, well, that's kind of not very exciting. But on the opposite, that's actually very exciting that we saw that switching the Python PyMalloc allocator for mimalloc did no difference. And the reason is because PyMalloc is specifically tuned to be very fast when you do these kind of very specific patterns that we do in CPython, like very fast object allocation at the allocation for objects that are very small. Like other general allocators like malloc, like from libc, glibc, they are very generic. They are trying to be the best possible allocators in all cases, which means that obviously it's not the best for specific patterns.
Right.
And the fact that the malloc was not as slow than PyMalloc is very interesting because mimalloc is still a very generic allocator in the sense that it doesn't. It's not branded as allocator for interpreted languages, right, or for things like that. So that speaks really good about mimalloc. It's not going to be like, wow, now Python is much faster. Obviously, we have all these features that you mentioned about this partial, and the nogil work needs it. But one of the things that we can do in the future maybe is to just remove all the code from PyMalloc because we actually don't need it. And it doesn't hurt in the long run to just use mimalloc all the time. Even meanwhile, we are actually transitioning to the free threading work, right?
Yeah, which brings me to when we had the global interpreter lock, the way you denoted that you need to synchronize something, like you just held the global interpreter lock, right? And that was in many cases done like for you, but in the NDC API, you had APIs to free the lock and to hold it again, and that was it. Now, if there is not a global lock, like, what are you supposed to do? So one of the changes that just landed super recently is critical sections. So something that you might remember from your OS classes at university, like, not super easy if you're really thinking about this, but there is now critical sections in the Python C API. Begin critical section on an object or two, and then you can end a critical section. So essentially helpers to replace the global interpreter lock with finer grained locking.
Right.
So you can provide similar guarantees to the GIL, right? So we actually have a better solution than just regular fine-grained locks because that kind of avoids some of deadlocks that we can have not all of them, but the one thing that it can fix is, for example, when you are nesting critical sections, like that will actually automatically do the interleaving that is necessary for this to work. So that was a very impressive commit. We have the PR with quite a lot of comments on the review there. So yeah, impressive work just added just now.
Right, that is very good, and this is a very tricky thing, right? Just for clarifying what the problem was, is that if you say, oh, now that we don't have the big lock, let's substitute that by smaller locks, maybe it comes as a surprise to a lot of people, but if you have a regular lock and you lock it twice, the second operation actually blocks forever. It's not an op. So if you have a place when you acquire the GIL and then you have another function called inside that place that also acquires the GIL, right now that doesn't block forever because the GIL has some specific semantics for that. But if you substitute this in by normal locks, then the second call will block forever, and we don't want that. And these critical sections allow you to basically extensions to behave more or less like when the GIL was there. Without having to implement all the regular locks, it skips the performance problem and also the lock problem, which is very good. Some other change that I'm very excited about is the fact that subinterpreters can now share tuples, which may look like a very small feat, but it's the beginning of what I hope is a very fantastic trend, because right now, as you know, if you want to share objects from one subinterpreter to another, and subinterpreters are this new thing that we added in Python 3.12 that Eric's now worked really hard to get there, and others. So this is an alternative to multiprocessing.
So clarification, subinterpreters have been there for quite a while. What they have now is they have... Each own has its own global lock.
Its own GIL. Yeah. Yes. Sorry. That's the correct thing. Yeah. People say that, but then on the other hand, the API was really restrictive, right? I know that what is the name of this package that runs web servers? Whiskey.
ModWhiskey.
Yeah. Yes, ModWhiskey. So I think those people were using subinterpreters even from long ago.
Right.
But anyway, now they are more feature complete. Now they do the actual thing that you expect them to do, which is run independently of each other. So you can actually use them as an alternative to threads and processes. But if you want to send objects from one to the other, or use objects from one subinterpreter to another, you need to serialize those objects. So you need to transform them to bytes and decode them in the other side to make a copy. So not as exciting as threads that can share the objects, but now. With this change, some interpreters can share tuples. There is some caveats because the same way you can, tuples are hashable unless they contain non-hashable objects. You can totally put a list inside that tuple, and then it's not hashable because the list is not hashable. So if you have tuples that contain, other tuples, they can be shareable as long as the tuples themselves are shareable. And then you can have other types that are shareable, like strings, bytes, integers, floats, all the kind of immutable stuff. And this is very exciting because the more objects you can start to share between subinterpreters, the less copies you need to do. So it's not only faster, but also uses less memory. And the more it appears to be a very, very enticing alternative to multiprocessing.
Right, yeah. So as long as they are immutable, right, then essentially both interpreters can read the data correctly. And before we only had basic types, right? And now tuples is the first one that allows us to actually organize information, right? So it's some structural, data structure. But the funny thing is, obviously a tuple can hold whatever. It can hold a list. It can hold an object. So what happens if you try to actually share an object like that? And this is handled. In that case, there's going to be an exception saying well, I'm sorry, but this particular tuple is a little too complex for now. But still, you can have nested tuples, and if those tuples end actually having only simple types that are supported right now, right? So bytes, integers, floats, booleans, and none, and strings. Floats were just also recently added. So all of this you can already use to build non-trivial applications. This is a start of subinterpreters being actually usable for production code.
Right. And we have some exciting changes actually on the evaluation loop, right?
Right, yes.
Can you tell us about those?
Right. So we already talked about our trip to Brno and how there's talk about having a JIT in Python. So how does that compose with what we already had? So now we call the entire interpreter as we had before, including the specializations that we knew before, as tier 1. This is the classic standard old interpreter that we had, which executes the Python bytecode right? This is the kind of tier 1 simple thing. Now we have this new tier introduced called tier 2, which does not run Python bytecode. It runs micro instructions. We call them uops. And those are the basis of what we're going to actually just-in-time compile later with the copy and patch approach that we were discussing in episode 1. So what we had so far already after the sprint was tier 1 and tier 2 coexisted, but they were separate files. They could call to one another, but Mark Shannon was unhappy about the state of things there. And the reason why was he observed that a function call is kind of limiting in what you can do because it can accept many arguments, but it can only return one value at a time. And this was not really good for a bunch of reasons. So now Guido made this big change where he brought the tier 2 interpreter inside PyEval frame default. So now this is kind of intermingled. It still looks reasonably, readable, even though now this file is larger than it was before. But that will allow tier 1 and tier 2 to switch more granularly when that's needed, right? You can follow some of those ideas that the Faster Python team has on this in their own bug tracker that they have for kind of planning their work. But yeah, like that was a very exciting change to see just this time around.
Right. So another change that, is in the making, but I wanted to mention it here just because I was very excited, is that so as you know, Python 3.12, we added support for the Linux perf profiler, which is like super exciting. And, we, like a lot of people are starting to use it actually. Like I heard from Meta, they are playing with it and they are actually contributing some ideas. But unfortunately, one of the caveats here is that you need to compile CPython in a specific way. You may already be already compiling it this way, but a lot of distributions don't, which is with these frame pointers. That doesn't matter. We are not going into detail. It's just that it has this restriction that you need to ensure that when you compile CPython, you add these frame pointers. And unfortunately, this makes Python a bit slower. But for most of these profilers, you need these frame pointers anyway. So it's almost like a require for these profilers to work. This includes others other than perf called eBPF based profilers. But anyway, so the perf can actually work without this, and instead of like doing the super fast, frame pointer traversal to get the whole stack, it uses DWARF information, which is the debugging information that is included in binaries. This is a much slower method because when perf is using this DWARF information to retrieve the stack, so the who call who when some event happens, it needs to copy the entire stack. This is not the stack of pointers. This is the stack of everything. So the data and everything that is on the stack of the process that is running, and then later it analyzes this stack, reads the DWARF information, and tells you who is calling who, and it shows you into the flame graph or whatever, right? But unfortunately, the work that we did in Python to make it compatible with perf didn't work with this particular case because we are JIT compiling code to make it work, and we are not including debugging information from the JIT. So for a long time, I tried to search a solution that is not just doing this debug information, because let me tell you something, creating that debug information is just hell. It's real hell. It's extremely annoying. It's extremely undocumented, and the failure mode is it just doesn't work. So it doesn't tell you, oh, you forgot here a number 3. It's not no. That's the only answer that you get from the tool. So I was talking with Carl from the PyPy team. And we were bouncing ideas, and we were checking how PyPy works, because somehow PyPy more or less does some stuff we discovered, and then it was less exciting than initially looked, but it was super helpful. And we started analyzing how other VMs do this. For instance, the V8 engine, which is the all the VM that JavaScript uses, right? Like the Google Chrome, I think is the one using V8, right?
Yes.
Right. So it turns out that the V8 people actually talk with the perf team to implement a bunch of specific interfaces that seems that they only use, which is kind of cool. And I was analyzing the code in V8 how to do this, and I found an extremely hacky way to kind of trick perf with half DWARF. So I actually, sit down and wrote the DWARF thing. It's just half of it. And it turns out that with half of it, it kind of works. And I'm super excited because maybe for Python 3.13, you can actually use it. It's still inferior to half frame pointers, but at least it works. And you can actually use perf with the DWARF information by using half debugging information.
You already mentioned this on this podcast, so it's not maybe. Like now you have to make it work for 3.13. It's not an option.
Right. I'm 99% it will be there. I just need to double check that everything works, because let me tell you something. When the failure mode is just the tool saying no, the moment it works, man, you just like celebrate like crazy, man. I was just not believing it.
I can imagine.
So I still need to, I sat down the computer, is there, sitting there on the hard drive, nicely there. So I just need to boot it again and check that I was not, like hallucinating things, and actually it is doing the thing. But if it's doing it, I'm quite sure it probably will go into C13. So I just need to do the PR.
Speaking of Carl Friedrich, he did add a thing to CPython now that doesn't sound like it's super awesome at first, but it is. So now Unicode data code point names are stored using a DAWG, or really a directed acyclic word graph. But we do have a DWARF.py file now in the CPython repository, which Brand found amusing. I also found it amusing. So yes. But essentially what that means is...
what does this do?
Yeah, it's like a smarter, more space efficient prefix tree. So
the real one, no? Right.
Yeah.
Right.
So it's this directed acyclic word graph, and what it can do is it will use fewer vertices to store the same data, because it can just reuse the paths that you already had. So it's pretty efficient. But what that means is the names are now encoded into packed strings. So, essentially just, and that represents the entire machine needed, the finite state machine needed to recognize whether something is a valid name, but also to map a name to an index. So essentially it still works as it was before. If you needed to know which code point is called, I don't know, a snowman or whatever, but now this is smaller by over 400 kilobytes. Doesn't sound like much, but if you actually have all this in memory and multiple times over because you have multiple processes, or if you are moving Python to somebody's computer via web because you're using WebAssembly or you're using PyScript, now you can use nearly half a meg less for essentially the same information. So that's pretty impressive. I think this will actually help us spread Python in the web use, which I'm very excited about. So that was a pretty cool change. It took us quite a while to review it because the algorithm to turn our raw data from downloaded from unicode.org into this form is pretty complicated, but then you also have to implement in C this lookup algorithm that actually uses this representation to check whether a name exists or not. And as far as we can tell, because there is a test literally in the test suite checking all the names. So we're actually finding all the names that are in the Unicode database and checking that that works perfectly fine. So this we know, like maybe there is going to be a bug where we would actually return a code point for some name that is invalid, but some random combination of characters would actually yield a code point, even though it shouldn't be found there. But it is extremely unlikely from the code review that we've gotten. Like we asked Dennis Sweeney, also like a heavy hitter contributor, to review this code. We're pretty confident it's good, but it is essentially harder to prove a negative than to actually prove that it works, like with the test. There is no test possibly that we can write to say no possible combination of characters that is not in the Unicode database will yield a code point. So this was a challenge to review.
Right. So thanks everyone here, and thanks Carl for the help there. I think we need to mention the last things a bit faster, just not to go over like 6 million hours in the podcast as much as we like to talk. One change that is quite tricky actually to produce, I'm very happy that we are doing it, that Thread.join now waits for the actual underlying thread before exiting. This may seem like why is this important? Like, at the end of the day, when you call join, or what CPython does is that it waits for all the Python code to finish. And then, after that happens, the thread is still there because Python didn't actually create the thread. It uses like all the threading APIs from the underlying OS, which are different in Windows, macOS, and Linux. And pthreads and not pthreads and whatnot. But at the end, when Python finishes, the thread is going to die, but it still does a bunch of things before that, right? So it still lingers there, and we never wait for it. And it really didn't matter because this code actually is very small. But now, there is a bunch of things that we're doing on Python 3.12 that make this change quite important. For instance, in Python 3.12, we are now emitting warnings if you call os.fork and there are threads around. And why is this important? Well, because os.fork only it creates a new process, a new copy of your process, but only the thread that is running.
Yeah.
And this is very important. It's very important because if you have logs, for instance, lying around and other threads have the logs, those logs are now useless. And you can deadlog if they were in a log state. So you don't want that. So right now we warn, and then you call os.fork, we say, man, you have all these threads running around and those are not being forked, right? But obviously, if we were not able to deterministically know if Python has finished for real with the thread, this warning is not the best it could be. So now we have all the machinery needed to know when the thread is really done and the OS has finally finished with the thread. So the warning makes sense, and we can know it deterministically.
Right. Yes. So now we will be able to actually write correct code that we know is correct and does not raise the warning. So 3.12 is going to be just a little annoying in that regard because it does raise the warning, but in some cases we won't be able to actually make sure that there is no warning raised. Right. We actually have something new for you as well, which is a short section on a PR of the week by each of us. So this doesn't happen every time. We don't actually produce code every week. I review and do internal tooling and set up buildbots and whatever. But every now and again, there would be a change that I would be kind of passionate about. Pablo as well. He already talked about his, but he gets another one, I guess.
Wow.
Let's be fair. Let's give you another one.
Wait. Sorry, I have to intercede.
Yes.
I think we are still in the bounds of legality because this section is called PR of the week, and it's talking about a PR that not only is already there, but is also merged, hopefully. But the perf work that I mentioned is not even a PR. so the work is there, but it could have never been a PR of the week, you see? Totally legal.
I'm not a lawyer, but I somehow find this objection.
Pablo did it again.
But since you're already talking, you might as well start with your PR of the week.
What a segue. Okay. So my PR of the week, I will spare you the number, is about speeding up traceback object creation. Turns out that some time ago, man, this is so funny. So some time ago, we have this funny bug report, I think for 3.11, and obviously also 3.12, that if you raise an exception, right? So you say raise, because you do it or because it happens. So for instance, you access a list out of bounds, or because you say raise something. Turns out that if you measure the time the interpreter takes to raise the exception, it was longer the more instructions there were in the function. So if you raise an exception at the beginning of the function, it was much faster than if you raise the same exception at the end of the function.
Interesting.
Man, this was crazy. There is some data here that I have. So depending on the number of statements that you have in your program, obviously the reality doesn't really measure in statements, but it gives you a good proxy. Like with 100 statements, raising an exception in this particular system takes 2.7 microseconds, but with 100,000 statements, it takes 2,700 microseconds. So it's just a lot. I mean, it's not going to cause a huge amount of difference, but the fact that the raising an exception, the time it takes, it changes depending on the position, is quite surprising first, and then a bit concerning. Turns out that what's happening is that, when we raise an exception, we need to tell you the line number of the, in the source code that raised the exception, because when we show the traceback, you can look at this information and we can show you the number. And since Python 3.11, because we did this work for, ensuring that we store column position so we can show you the fancy tracebacks, turns out that information that maps from bytecode position to the line number is encoded in this compressed table, because there is a lot of data there and we cannot just have it lying around because most of the line numbers are going to be the same, blah, blah, blah. So, there's this compressed data, and when we need to find what is the line that corresponds to a certain bytecode instruction, we need to go there and then decompress the data and find where is the line number. And this obviously takes time the farther you are, because when you start decompressing the data, if it's one of the first instructions, then you don't need to decompress the whole thing, right? Because, it's going to be very early in the stream of data. But if it's in one of the longest instructions, you need to decompress everything, because the way the compression works makes chunks farther away depending on previous chunks. So you need to decompress the the start. So that was what was happening. And the fix was actually quite simple. It was just making this calculation lazy, because you actually don't need the line number until you need to show the line, and that only happens if the exception bubbles up to top level or if someone just happens to ask for it. So we transformed the line number into a descriptor, which triggers lazily, and just raising exceptions doesn't trigger the calculation on line numbers. It just only when the exception bubbles up, then it just triggers it. So we only do it when it's strictly necessary. That was a fun change to do, and it makes Python a bit faster. Actually, it's measurable in PyPerformance, which is quite cool.
Yeah, I also have a change that makes something faster, but it's mostly for our internal use. So there's this PEP 669, which is a really nice way to monitor Python. It's faster than tracing. It is more pluggable with a nicer API, and so on and so on. So now we are using it to power test coverage of the stdlib library. So this needed some support that I added at the sprint, with the ability to run code before site.py. So if you were confused before, what am I talking about, about site.py, in this episode, fortunately, we are past this and you understand everything, right? Site.py is this strange moment where suddenly we start importing Python modules and we're enabling site packages and so on, and doing a bunch of other stuff, right? So if you really want to measure coverage correctly of the stdlib library, you need to plug into that just before site.py is executed. So that functionality was added before, and now the actual change to change our test suite, to change our test runner, to allow to use this, that I did now. And the fun thing about this is that this is already measurably 5 times faster if you are using sys.monitoring compared to what we had before. So the trace module that you can find in stdlib library, that's what the regression test suite uses internally. And that is still left for when we're running tests sequentially. But a new thing that was not possible before was gathering coverage when you're using worker processes. So if you run your regression tests with -j, so with many processes at the same time so that it's faster, now it will collect pieces of coverage and then combine them, aggregate them together, and just present you with a correct summary of everything. So this allows the entire coverage gathering to be so much faster that, let me just leave you with some numbers. Before, I don't think anybody was using coverage reporting on the entire test suite because it only worked in sequential mode and used the slow trace module. So that took a few hours to complete. It took over 2 hours to complete on my M1 Max Mac. But the problem was that I couldn't even finish the tests, because if you're running them in sequential mode, every time something happens that crashes the interpreter, well, your test runner also crashed, so you didn't finish. You actually cannot show any sort of coverage. So I tried Linux, I tried Macs, like different kind of versions and so on, and found that there was some issue with gathering coverage and with sequential runs on every platform I tried. So I'm pretty sure people were only using this for pointed coverage results for a particular library and not running it over everything. And now you can run it, and with just J1, meaning you're only using one worker process. Like this runs in 9.5 minutes for me. So it's like it's pretty cool. Like it's pretty fast.
My strategy is that now people will think you added the sound and not myself.
That's all good. Yeah, so kind of it is fast enough that I imagine people will start actually using it now. So obviously what we need is not some report that tell us like, oh no, we just need this number to be 100% all the time, even though for a programming language, we would have really higher standards than most external projects, right? But what we really want to know is when we're doing larger changes over tests or over libraries, some refactors and so on, that before and after are not regressing our coverage too, right? So like that way, I do hope that people will use this more accurately and like faster and so on and so on. So yeah, like that was a change that I was very happy to see because I mostly wanted the coverage numbers to just be correct, and the additional speed and support for worker processes or just like cherry on the cake, but that cherry is almost as big as the cake for me like at this point.
Oh, right. I think this change is super cool. I think it's super cool. I'm so happy because like indeed, like I was one of those persons that were not running this just because like it just takes forever and like it has so many failure modes. So I'm very happy that now we can actually leverage this. Maybe we can even add it to the CI in some way or form.
We should, yeah. Let's do that. Okay, that's everything we have for today. We already passed the hour mark again. One episode is going to be under 60 minutes, and then you'll know we really ran out of stuff to talk about. But no, not today. Not today, Satan.
Not today. Thank you everyone for listening. We will love if you also reach to us to tell us what you think about this episode. So maybe, you want more or less. What topics do you find interesting? More super technical details, more high-level battle stories of all people. What do you find interesting? Tell us the way you prefer. And that's everything we have. So thank you for listening.
See you next time.
See you next time.